So if two functions are inverses, then we know the following is true. We know that f of g of x, so I should get two functions f of x and g of x are inverses. And then we know that f of g of x and g of f of x are both equal to x, meaning the functions undo each other. F does something to x, right? So you start with x, f does something, g undoes that, and we end up back at x. Or start at x, g does something, f undoes what g did, and you get back to x. So that's the idea with inverse functions. Another thing that's true, which I already said, I'm gonna write it down. If two functions are inverses, then their graphs are, what's the best way to say this? Their graphs, I like to say, are mirror images about the line y equals x, but you can say their graphs are reflections of each other across the line y equals x. There are lots of examples of this. We'll draw a few of them here. So again, just to say it again, inverse functions, f and g, f of g of x equals g of f of x equals x. And inverse functions, their graphs are mirror images or reflections of each other across the line y equals x. So one of the examples I've got in the notes there, which I'll draw here, are the graphs of e to the x and natural log of x. Let's see if I can draw this fairly well. Sure. So when I'm trying to draw e to the x and the natural log of x, there's a couple points I try and graph. Actually, first, before anything, I'm going to graph the line y equals x. And I'm drawing it dashed because it's not really one of the graphs I actually want to. It's not a slant asymptote. I'm just drawing it like this because it's not super important. It's a line that we're reflecting about. So e to the x, looks like your usual exponential graph. It goes to the point 0, 1. And then it also, right, I'm going to try and plot another point just to make it look a little bit more precise. And it goes to the point if x is 1, y is e. So f of 1 equals e to the 1, which is about 2.7. So if I plug in 1 for x, I'm going to get like 2.7, which is maybe like, I don't know, it doesn't have to be exact, but it's maybe right about there. And then it's going to have a horizontal asymptote to the left. So it's going to look kind of like this. That's the idea. No vertical asymptote, right? It keeps going to the right and up. And then the logarithmic graph, y equal to the natural log of x. I know I have the intercept 1, 0. In fact, let me label these points here. So this point here is 0, 1. This point here is 1, comma, e, approximately 2.7. And then for y equals natural log of x, I'm going to have the point 1, 0, which will be right here. And then I'm also going to try and graph the point when x is equal to e. So if x is equal to e, I should call this g of x, sorry. G of e equals the natural log of e, which is 1. So when I plug in e for x, I get 1 for y. So e again is about 2.7, y is about 1, so I'm about right there. Vertical asymptote at x equals 0. And here's the point, e comma 1. And then I think you guys can see, I hope you can see, that these graphs are mirror images of each other across this line. If you take this one and you flip it over that line, you get exactly that graph there. And we can really see this by the fact that this point, if you flip it over this line, is that point right there. Also, again, the picture's not perfect. And this point here, if you flip it over that line, is that point right there. So when you flip a point or reflect a point across the line y equals x, you interchange x and y, which is exactly how we find inverse functions, by interchanging x and y and then solving for y. So the thing about this that we're going to use specifically today is the fact that this allows you to find the range of a function by finding the domain of its inverse. So if f and g are inverses, then we know that the range of f of x is equal to the domain of g of x, and vice versa. The range of g of x equals the domain of f of x. So if we wanted to find, say, the range of f of x equals e to the x, well, we could pretend like we didn't know it. Oh, what is the reflection of 1e? It's e comma 1. Sorry, yeah, I know that. Sorry, the green is not always easy to read. I apologize. I should use them. I have a blue. The problem is I have lots of green pens and I don't have a lot of blue pens. Yeah, that's e comma 1. You can kind of see that better now. So I can find the range of this function here by saying, well, it's the same as the domain of this function here. And the domain of natural log of x is 0 to infinity, exclusive of 0, right? You get all the positive numbers, which means the range of the inverse function, f of x equal to e to the x, is the same. It's everything from 0 to infinity, exclusive of 0. And that's the whole idea. We're going to find the range of functions by finding the domain of the inverse function using the usual domain rules. That you can't divide by 0, you can't take the square root of a negative, you can't take the log of a non-positive number. Well, let's look at some other graphical examples. I feel like we did an example similar to this before, but it's worth doing more of the same, right? It's good to get practice. So let's say, and I'll use blue instead of green here. Let's say I have the functions, what have I got? F of x equal to 2/3 x minus 4/3, or if you prefer 2x minus 4 all over 3, and the inverse function. So again, if you want to find the inverse function of a line, it's actually usually pretty easy to talk it out. Meaning, think about what this equation is doing to x in order. So first we take x, we multiply by 2, then we subtract 4, then we divide the whole thing by 3. So to find the inverse, I'm going to undo all those operations in the opposite order. So the last thing I did was divide by 3. So the first thing I'm going to do is I'm going to multiply by 3. The second to last thing I did was subtract 4. So I'm going to add 4. And then the very first thing I did here was multiply by 2. So I'm going to divide by 2. These functions should be inverses of each other. This one takes x, multiplies by 2, subtracts 4, divides by 3. This one takes that result, multiplies by 3, then adds 4, then divides by 2. They are inverses. Let's graph them. So if I was going to graph them, I would probably find the intercepts. So to graph f of x, the intercepts are going to be, well, if x is 0, the y value is going to be 0 minus 4 over 3. And if y was 0, so let's see, if I set this equal to 0, 2x minus 4 over 3 equal to 0, 2x minus 4 equals 3 times 0, 2x equals 4, x equals 2. So those are my y and x intercepts here. And then they should be flipped, right? These coordinates should be just interchanged with x and y values. Well, let's double check. Here, the y-intercept is going to be, so if x is 0, 0 plus 4 divided by 2 is 2. And if y is 0, I can do a little bit of work. 0 equals 3x plus 4 over 2 multiplied by 2. Subtract 4, negative 4 equals 3x divided by 3. Yep, you get negative 4/3. That's a good sign. These are inverses because the x and y intercepts are switched. Let me talk about how I would actually graph this. So, try and be super precise here. So in the interest of being super precise, I'm going to plot the point 2, 0. But to be honest, 0, negative 4/3 is not something I'm great at getting exactly right. So I would rather maybe pick something like x equal to -1. Because if x is -1, then 2 times -1 is -2. -2 minus 4 is -6. And -6 divided by 3 is -2. So I plug in -1 for x, I get -2 for y. And then I can draw the line that goes through these 2 points. Which, okay, this is not my best line ever. That is not a very straight line. Sorry. But hopefully you can see, like, I'm pretty close to hitting the right y-intercept here. Maybe it doesn't look exactly right. And things are not going to look perfect every time, or any time, maybe. In the same way, I would graph the blue line. I would say, okay, well, I'm going to do the point 0, 2. And I'm also going to, instead of doing negative 4/3, 0, which is like here, I'm going to go ahead and plug in -2 for x. If I plug in -2, 3 times -2 is -6. -6 plus 4 is -2. -2 divided by 2 is -1. So I get this point here. So then I'm going to draw that line there. I'm going to try and draw the line. It's no fun when you miss. That's a little better. So there's those lines. And they do totally look like the reflections of each other in the line y equals x. Flip this line over that line, over this line, you get that one, and vice versa. And again, the point 0, 2 here is reflecting over to the point 2, 0. And the point negative 4/3, 0 is reflecting over to the point 0, negative 4/3. We could talk about domain and range here, but it's a little bit silly because both of these functions have the entire domain and the entire range, right? The domain of f of x, there's no issues, right? There's no division by 0 because the denominator is just 3. There's no square roots, there's no logarithm, so the domain is everything. Here, it's also the domain is everything. And since the domain of this equals the range of this and vice versa, the range of this is also everything, and the range of this is also everything. So they both have, and basically any line that isn't a vertical line or a horizontal line will have a domain and range that is all real numbers. Like I've written here in my notes, another example, but I've literally drawn the same graph. That's smart. Look at my other notes. I've got 2 versions of notes here. 1 second. Okay, now we're good. All right. So let's look at this next one. So I am going to want to see the work for this, even if the answer is maybe easy to guess. Okay, so let's look at this example. Let's look at f of x equal to x plus 3 divided by 3x minus 5. And I want to find both the domain and the range without graphing. Domain should be relatively straightforward, right? We are going to say, well, we can't divide by 0. So for the domain, we say, well, look, I need to make sure that 3x minus 5 equal to 0 is excluded. So solve this. 3x equals 5, x equals 5 divided by 3. I literally want every x value except for that one. So on the number line, I want not that. I want all this, I want all this. We always go from left to right when we're writing our interval notation. So I'm starting over here at negative infinity, all the way up to 5/3, excluding 5/3 of the parentheses, union 5/3. Now, you might be able to guess what's not in the range, because if you look at this function, you might know that the horizontal asymptote is 1/3, right? The degrees are the same, x to the first and x to the first. I do want to point out, I saw a few people on various places, just a quick aside here. I've seen people before say that if you have like y equals 1x squared plus 5 over 1x squared plus 3. I've had people say that the horizontal asymptote is y equal to 2 divided by 2, which is 1. It's 1, but it's not because it's 2 divided by 2. It's because the degrees are the same, and it's 1 divided by 1. Right? So it's always the coefficients that you're dividing, not the powers that you're dividing. The powers are the same, and you're dividing the powers, you're always going to get 1. So here, the horizontal asymptote would be y equal to 1/3, because the degrees are the same, and we're dividing the coefficients. And that's actually going to be what's not in our range. Now, again, I should clarify, right? Sometimes your graph can cross a horizontal asymptote, and it will be in the range. This graph does not cross its horizontal asymptote. So that value, and only that value, end up being excluded from the range. But we don't have to know any of that to be able to find the range. We just have to be able to find the domain of the inverse function. So let's find the inverse function through our usual process. Step 1, which is not really much of a step, right? Y equals x plus 3 over 3x minus 5. Step 2, interchange x and y. When you interchange x and y, you are literally finding the inverse. I'm curious if Desmos would show us this. Let me take a quick look at something real quick. Sorry, 1 second. I just wanted to see if I can show you guys a thing or not. Let's see if I do x equal to, yeah, I think it will. Let's do some, yeah, so I should say, hey, just the domain of the inverse function will give us the range of the original function. We'll graph it in a second here, but I will show you guys here. So now we're going to solve for y. So multiply both sides by 3y minus 5. So you get 3y minus 5 times x equal to y plus 3. And then distribute the x, because again, we're trying to solve for y, but y has to be a function of just x. So I'm going to have 3xy minus 5x equal to y plus 3. Factor out, don't factor out. So here's where people, I haven't seen anyone do this this quarter, but definitely in past quarters, I've seen people do this and then factor the x back out and divide and end up back where you started. Don't make that mistake, right? We're trying to solve for y. So bring the y's to the same side. 3xy minus y equals, bring the not y's to the other side. Factor out the y. Y times 3x minus 1 equals 5x plus 3. And then solve for y. Y is 5x plus 3 divided by 3x minus 1. And you'll notice for this function, so for, let me write it over here. So for f inverse of x equal to what we just found, 5x plus 3 over 3x minus 1, we can see that the domain of f inverse, well, x can't be 1/3, right? If you have 3x minus 1 equal to 0, 3x equals 1, x equals 1/3. So we don't want x equals 1/3. We're excluding that. So we're exactly saying, okay, for the range of f, we want everything except for 1/3. So negative infinity to 1/3 union 1/3 to infinity. So again, I'll repeat, the range of the original function is the same as the domain of the inverse function, and vice versa. The domain of the original function, which doesn't include 5/3, is the same as the range of the inverse, which doesn't include 5/3. Let me show you guys one thing, just because I think it's kind of neat. So on Desmos, which I think is useful, if you were going to graph the original function, we do that one first, which is y equal to y equal to x divided by x plus 3 divided by 3x minus 5. There you go. So you can see, or I will show you, that we have a vertical asymptote at x equal to 5/3, and we have a horizontal asymptote at y equal to, what did I say, 1/3? Yeah, 1/3. Great. But we can also graph the inverse. And now you can graph the inverse, I think. I didn't actually check. I checked one thing, but wasn't this. By just interchanging x and y. So I'm going to say x equals y plus 3. Hope this works. Divided by 3y minus 5. And look, there's the inverse function. It's the same as if let me turn these other ones off for a second. It's the same as if I actually graph the inverse function, which is 5x plus 3 over 3x minus 1. Let's check it out. Y equal to 5x plus 3 divided by 3x minus 1. Look, they're literally the same function. Turn one off, turn it back on, turn the other one off, right? They're the same. And you can see that this function has a horizontal asymptote of 5/3, sorry, and a vertical asymptote of 1/3. So the domain and the range have interchanged, right? The domain of this function, y equal to the inverse function, 5x plus 3 over 3x minus 1, which excludes 1/3, is the same as the range of this function, which excludes 1/3, and vice versa. So the neat thing here, which I just want to say again, is that you can totally graph the inverse by just interchanging x and y. So for example, if I wanted to graph the inverse of, say, y equal to x cubed, yeah, I could find it. I could do x equals y cubed and then take the cube root of both sides. But I could also just say x equals y cubed. And there's the inverse function. Kind of neat, which is the same as y equal to x to the 1/3 power, or the cube root of x if you prefer. Sorry, it's getting a little messy here. The other thing that this is actually kind of helpful with, which I just want to point out, and then we'll get back to the regular scripted program here, is that for functions that are not invertible on their own, you can see why they're not invertible. So there's y equals x squared, which isn't invertible because if you try to switch x and y, you don't get a function, right? This thing here fails the vertical line test. But if we strict the domain here to be x greater than or equal to 0, by the way, if you're trying to do greater than or equal to 0 in Desmos, you do the greater than, and then you just type equals after that, and it'll give you greater than or equal to. That gives me the right side. But now for this one, I have to then say, well, here then, y has to be greater than or equal to 0. Oops, y should be lowercase y. Like that. Graphically, exactly what we're looking for. Which is the same as saying y equal to the positive square root. Square root of x. Right? That blue graph and that green graph are the same. Whereas y equal to the negative square root of x would be the other part, which we don't want. Right? So this and this are the same as this. right? There's the blue, the green part is the upper part, the purple part's the lower part. X equals y squared is all that. So, right, you can kind of see why some functions, when you aren't one-to-one, right, this function fails the horizontal line test, its inverse relationship fails the vertical line test. So we need to restrict it so that its inverse passes. All right, let me get back to the class, but hopefully that was somewhat useful to see. I think it was. Where did I go? Cool. What time? I got 20 minutes. Well, I got a lot of things to say in 20 minutes. Okay, that's all right. So the rest of the examples are mostly just finding the domain by using the inverse function. Finding the range by using the inverse. Sorry. Okay, so more examples. I certainly think it is worth your while to look at the graphs of the function and the inverse, but you don't have to. But if you wanted to, so like, let's look at this function for a second. So if I'm looking at f of x equal to the log base 3 of x plus 3. And I really just want to find the domain and the range. If you wanted to throw this into Desmos to see what the graphs look like, you could do y equals log base 3 of x plus 3. And then to find the inverse or to graph the inverse, instead of actually trying to solve for it, although we will solve for it, if you're just trying to see the graph, the inverse graph, you can just say, well, that's going to be x equal to log base 3 of y plus 3. And not even solve it. And it would totally give you the graph of the inverse, which is kind of cool. We're going to solve it, but okay. So domain here, for a logarithm, we know that the insides have to be strictly greater than 0. So that's going to leave us with x is strictly greater than -3. On the number line, we want everything not including but to the right. So I want my domain here to be everything from -3 to infinity. Great. For the range, we have to find the inverse. You could, I mean, it is valid to think about the graph, but I'm going to show you the non-graphical way of doing it. So let's find the inverse. So I've got y equal to log base 3 of x plus 3. I'm interchanging x and y. So x equals log base 3 of y plus 3. And then I'm going to rewrite it as an exponential because I'm trying to solve for y. So 3 to the x equals y plus 3. And then y equals 3 to the x minus 3. Okay. This function has no domain issues. This function, x can be anything. There's no logarithms, there's no roots, there's no fractions. So this function has domain, all real numbers, which means the range of this function is all real numbers. You could also see this if you graphed it. But again, right, we're trying to do it the other way. But graphically, right, it's a logarithm function. It's been shifted 3 to the left. And it looks like this. It goes all the way down to negative infinity. It goes all the way up to positive infinity range-wise. Yeah. Let's look at another example. I guess I should point out here. Sorry, one sec. I should have said at some point here, right? F inverse of x is 3 to the x minus 3. So it's interesting here, right? I'm kind of thinking of the original function as log base 3 of x, and then I shifted it 3 to the left. The inverse is 3 to the x shifted 3 down. So a left shift when you do the inverse becomes a downshift. A right shift when you do the inverse becomes an upshift. Let's look at another example. Maybe if I can click on the right thing. Can I click on that? Okay. So sometimes some things will require a little more, that's what I'm looking for, a little more care. I feel like I want to give you one more. Let's see, do I have one more example that's good? And so yeah, let's look at this one. So let's find the domain and the range of this function, which might be a little different. So yes, finding the inverse is one way to do it, to find the range, to find the domain and the inverse. Sometimes that's not the whole picture. I'm going to change the example. So I'm going to leave the example there. Fine. I'm going to do this example. Let's do x squared. Yeah, I'm like, what do I want to do? I don't know. Minus. Sorry, my brain's just like, James, think of any example that'll work. Sure. Minus 9x plus 20 divided by x minus 4. Find the domain and range of that. Well, we know it's not in the domain. X can't be 4. So our range is, our domain is everything except for 4. I can draw 4, really. There it is right there, 4. So it's domain, everything but 4. The problem with this function is you can't find the range in the way that you might think you could. This function doesn't invert so nicely. I mean, it is invertible, but as written, that would be really hard to figure out, right? So like if I was going to switch x and y, like do y equals x squared minus 9x plus 20 over x minus 4, and then switch x and y, I've got a problem here. And the problem is that solving for y here might be literally impossible. It's not, but it looks like it is. What we should do instead, before we really get into any of this, is we should see if this simplifies. And this does simplify. This factors as x minus 4 times x minus 5 over x minus 4. These cancel. So what you can say is your function, is the domain not at negative 4? Because the domain not at negative 4. So the domain is right. It's not has to do with factors. It's the fact that right, if you're trying to see where the denominator is 0, it's x equal to positive 4 because 4 minus 4 equals 0. So I could rewrite this function as x minus 5 with the caveat that x is not allowed to equal 4. Okay, we can find the inverse in one of two very straightforward ways. The most straightforward is to actually think of the graph. So you'd be like, okay, well, x can't be 4. So if I try and graph this line, y equal to x minus 5, it's got a y-intercept of negative 5. It's got an x-intercept of positive 5. But it's got a hole at that point right there. And the hole is x equal to 4. And if you could plug in 4 for x here, 4 minus 5 is negative 1. So the range is everything except for negative 1. Maybe you don't like that. That's fine if you don't like that. Another way you could do it, although I feel like it's a little bit weird, is you could do what we've been doing. You say, okay, well, I'm going to erase. Fine, I'll do the work up here. So you're going to take this function, y equals x minus 5, and you are going to enter and with x not equal to 4, and we're going to interchange every x and y. Even that one. So if I interchange x and y, I get x equal to y minus 5. But now y is not allowed to equal 4. Okay, that's kind of weird, but it works. Solving for y, I see that y is equal to x plus 5. But if y is not allowed to equal 4, well, if y were 4, x would have to be negative 1, right? If y is 4, 4 minus 5 is negative 1. So y not equaling 4 is equivalent to x not equaling negative 1. So look, we found the inverse, and the domain of the inverse is that x can't be negative 1, which means the range of the original function is that x can't be negative 1. We can also graph this. It's kind of funky. Actually, it's the, well, no, it's not the same graph. It's the reflection of this graph across the line y equals x. So it's got, I personally would recommend doing this one the way we did it first, by looking at the graph, seeing where the hole is, and that y value gets excluded from the range. But if you like this, that's okay too. So this one, you've got y intercept of 5 and x intercept of negative 5. Looks like this. These lines are parallel. They have the same slope. They are reflections of each other across the line y equals x. And then instead of not getting the point 4, negative 1, I don't get the point negative 1, 4. Right there. And these are totally reflections of each other across the line y equals x. That's kind of weird. Not gonna lie. I would definitely do it the graphical way, which these other two questions also kind of require more of a graphical approach. So I think most of the questions about this stuff are specified how you are intended to do it. If you're intended to think graphically, or if you're intended to actually find the inverse function. Well, let me show you a couple more examples. Let's look at the one, find the domain and range of, what do I got here? F of x equal to the square root of 9 minus x squared. So let's talk about the domain first of all. So for the domain, we need the insides of the square root to be greater than or equal to 0. Now here's where it's easy to kind of go in a direction that might not be great. I really don't want to do this. 9 is greater than or equal to x squared. Because then you have to take the square root of both sides, and you're kind of going to get, so if you're careful, it'll work. You do the square root of both sides. The square root of x squared is the absolute value of x. So the absolute value of x is less than or equal to 3, which means x is between 3 and negative 3. I don't love doing it this way. What I think is easier is to factor this. This factors as 3 minus x times 3 plus x. And then use the number line. Figure out where this is equal to 0. It's equal to 0 when x is 3 or when x is negative 3. And 0 is the only place where it can change from positive to negative. So if x is bigger than 3, like 5, 3 minus 5 is negative. 3 plus 5 is positive, and negative times a positive is negative. If x is 0, 3 minus 0 is positive, 3 plus 0 is positive, a positive times a positive is positive. And if x is negative 4, 3 minus 4 is positive, 3 plus negative 4 is negative, a positive times negative is negative. I want it to be greater than or equal to 0, which means I want it to be positive or 0. So I want all of this, none of that, none of that. So the domain here is negative 3 to 3 inclusive. How to find the range? Well, the problem with finding the range here is that we have to kind of know something already. So to find the range, I have to, well, I could try switching things in y equals square root of 9 minus x squared. Now, something we know about square roots, they always give you positive results. Right? The square root of 9 is 3, not plus or minus 3. The square root of 25 is 5. The square root of this is greater than or equal to 0, which means we already know that y has to be greater than or equal to 0. So when I switch these, x has to be greater than or equal to 0 because you interchange the roles. Then we can try solving for y. Square both sides. Add y squared over here. X squared plus y squared equals 9. Oh, hey, look, that looks like the equation of a circle whose center is the origin, whose radius is 3. Solving for y, I get y squared equal to 9 minus x squared. And then y is going to be plus or minus the square root of 9 minus x squared. Seems problematic. I don't like this plus minus. Here's what we really should do. We should say, well, look. We've got this, a circle whose center is the origin, radius is 3, except if it's the square root of 9 minus x squared, it's only the top half, right? Because here y has to be positive. So what we really have here is the top half of a circle whose radius is 3. Well, we can see the range of this, and we can see the domain of x pretty easily. The domain is negative 3 to 3, like we said. The range is, well, how low do the y values go? They go as low as 0, right? They can't be negative here because square roots only give positive results. The highest value is 3. That's kind of it. Yeah. Anything else I want to say about that? No, I don't think so. So again, a lot of times using the graph is kind of the way to go. Let's look at this last example. So, yeah. So this last example, there is a homework problem like this. This last example, I feel like, is a little bit challenging. Maybe a lot. It's kind of a lot challenging. So it's like, I'm leaving then. So I want to find the domain and range of this function. 20 over x squared plus 4. Now, I will point out that this function is not one-to-one. If you're graphing this, it's actually an even function. It's got even symmetry. If x is 0, you get 20 over 0 plus 4, which is 20 over 4, which is 5. And then if x gets bigger, the y values get smaller, right? If like x is 1, 20 over 1 plus 4 is 20 over 5, which is 4. And if x is 2, 20 over 4 plus 4 is 20 over 8, which is like 1 or 2 point something. And so on. So it kind of does this kind of deal. And I don't really, right? But then it also does the same thing to the left, which would be a problem if you were trying to invert, because if you switch x and y, if you reflect it across the y equals x line, the x and y things change and it starts looking like this. That's not a function. So what we're going to say is this is our function with the restricted domain of x being greater than or equal to 0. So that we don't have any of this, so that we don't get any of this problem part here. So that our inverse function, whatever it is a function. It passes the vertical line test. So let's talk about domain. For domain, we need to make sure there isn't division by 0. So does x squared plus 4 equal 0? It does not. X squared is always greater than or equal to 0. X squared plus 4 is always greater than or equal to 0 plus 4, which is 4. So the domain here could be everything except they already told us that x has to be greater than or equal to 0. So our domain here is really x is greater than or equal to 0. Okay. Let's talk about the range. The range is actually a little bit more difficult. Now, yeah, do I want to do this the hard way? That seems very hard. I don't want to do it the hard way. So here's the easy way, and then you can stick around for the hard way if you want. The easy way to do the range here is, again, to think graphically. Looking at this function, the biggest this function can be is when the denominator is the smallest. The smallest the denominator can be, well, we just said x squared plus 4 is always greater than or equal to 4. So the smallest it can be is 4. So the biggest range value, or the biggest y value, is going to be when x is 0. And y is going to be 20 over 4, which is 5. The smallest y value, well, let's see. This denominator is going to get very, 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 very large. Which means the denominator, which means the fraction is going to get super duper small. Can it ever equal 0? No. 20 over something that's whatever, it's really big, it's going to be very small, but not actually 0. Is it going to get super close to 0? Yes. So the smallest is 0, not including 0. Meaning our range here is 0 to 5. Exclusive of 0, inclusive of 5. And that's how I would encourage you to do this one. However, let me show you the longer way to do this if you really want to see it. You do not have to stick around for this. If you need or want to go, you won't be missing anything that's required. But some people might want to see the other way of doing this. So the other way of doing this is to use our process to find the inverse function. So here's the original function, 20 over x squared plus 4, where x is greater than or equal to 0. So here's the inverse. Sorry, I should say to find the inverse. We're going to switch x and y. So we're going to say that x equals 20 over y squared plus 4. And we're going to start off with the caveat that y has to be greater than or equal to 0. This is important. Okay, so let's see. I'm going to solve for y. So multiply both sides by the denominator. No, let's actually just, instead of doing that, let's just flip both sides. So 1 over x equals y squared plus 4 over 20. Multiply both sides by 20. So 20 over x equals y squared plus 4. Subtract 4. Y squared equals 20 over x minus 4. Okay, now we're going to take the square root of both sides. So I'm going to write it y first. So y is going to equal plus or minus the square root of 20 over x minus 4. Okay, watch this. Since y has to be greater than or equal to 0, because, right, the domain of this function has to be the same as the range of this function. So if the domain of this is that x is greater than 0, the range of this is that y is greater than or equal to 0. So since y has to be greater than or equal to 0, y has to equal the positive square root, so that you get positive values, not negative values. So that's how we're using this. And then we're going to solve this. So we need to get the common denominator here. So this is going to be y equal to the square root of 20 minus 4x all over x. Or I might write this as the square root of 4 times 5 minus x all over x. All right, there's our inverse function. We'll talk about the domain of this function very quickly. The values that are problematic here are 0 and 5. So if you plug in 0, you get division by 0, which means we definitely don't want 0. If you plug in 5, you do get it equal to 0, right? If you plug in 5, 5 minus 5 is 0, over 5 is still 0. So we actually want 5 because 5 will make it equal to 0. Now we have to test each of the intervals. So you pick a number larger than 5, like 6. 5 minus 6 is negative. 6 is positive. A negative over a positive is negative. We don't want that. We want the insides, right? So what I should say, I'm solving the inequality. 4 times 5 minus x over x is greater than or equal to 0. I don't want this stuff out here. Check in between 0 and 5. Pick the number 1. If x is 1, 5 minus 1 is positive. 1 is positive. A positive or a positive is positive. Pick something over here like negative 1. 5 minus negative 1 is positive. Negative 1 is negative. Positive divided by negative is negative. So I don't want this. I don't want this. I do want this. I want everything from 0 to 5. Oh, look. That's the same as what we saw graphically. It certainly is a kind of confusing process to do this, but it does work. It just requires a lot of kind of doing. So you don't have to do it that way, but you're certainly welcome to approach it that way if you want to.